Our focus today is on the concept of the elimination or reduction of emissions from the thermal reduction method of waste recovery. The Recovery 2.0 approach would eliminate stack emissions by the total containment and capture of the would-be flue gases and then converting them into a source for the recovery of elements and energy. Recovery 2.0 provides an opportunity to learn how to manage resources in a sustainable method by treating waste as a resource, while assisting with the world's demand for clean water and clean energy, using thermal reduction. The primary issue of combustion is mainly the concerns surrounding the emission of undesirable flue gases, and the reduction or elimination of the CO2 carbon footprint. Common emissions include such items as carbon dioxide, carbon monoxide, dioxins, and furans, sulfur and nitrogen derivatives, SOx and NOx, and a variety of other hazardous, toxic, or undesirable elements. To gain a better understanding of the process, we need to look at the life cycle assessment of the thermal reduction process and the oxidation combustion process. Performing a life cycle assessment to determine the carbon footprint on any thermal reduction process requires the review of at least three main criteria. These are: Scope 1, the emissions related to the direct thermal reduction process. Scope 2, the emissions surrounding the primary energy sources used to fuel the thermal reduction process, and Scope 3, the emissions derived from the use of the end products that are produced. In the thermal reduction process, an isolated retort chamber may be used to separate the feedstocks from the primary heat source. This is done in a controlled environment to ensure that no combustion of the processed feedstocks occur. The vaporization of waste materials, in the absence of combustion, avoids the production of undesirable combustion byproducts. A closed pipeline that controls the flow of the thermal vapors and that operate on a mass balance equilibrium recovery basis may eliminate atmospheric emissions. Any thermal reduction or combustion process that releases flue gas emissions into the atmospheric environment are considered to be Scope 1 emissions. This includes any incineration, gasification or pyrolysis process that does not operate as a closed system. These emissions are directly generated within the thermal reduction or combustion processes. In the case where the thermal reduction reaction chamber is separate from the primary energy source, an assessment of the heat source must be performed. This assessment identifies the source of the heat that drives the thermal reduction process and clearly establishes whether combustion is a component in that process. In the event that combustion is utilized in the energy generation stage, a clear certification of the combustion emission management process may be required. These emissions may be considered Scope 2 emissions, emissions that are caused when generating energy. When reviewing the end product outputs produced from the thermal waste reduction process, a clear designation of the intended uses of those products must be established. If the output products are declared as combustion-based fuels, the derivative emissions from those products must be considered. When these products are consumed or combusted, any emissions that are released into the atmosphere must be taken into account. These emissions may be considered Scope 3 emissions. Some claims of carbon neutrality from the use of green fuels may be made, but the underlying fact is, CO2 is emitted. To understand how and when these emissions are generated, we need to look at the oxidation-combustion process. Oxidation, combustion, and burning are all terms describing essentially the same process. Traditional forced air-blown combustion utilizes ambient air as the oxidizer. As the oxygen content of the ambient air is only approximately 23% by weight, then an additional volume of air is required to fulfill the complete combustion needs. Since nitrogen makes up about 78% by volume of ambient air, the combustion chamber is flooded with nitrogen, leading to the formation of harmful byproducts like NOx. In order to fulfill complete combustion, if enriched oxygen is inputted instead of ambient air, this would eliminate the abundance of nitrogen, and as such, the NOx emissions. Using a feedstock of enriched oxygen in the oxy-combustion process reduces the total volume of air required by 80%. On a sliding scale, the mass burning furnace produces heat, which may be extracted, which in turn can be used to generate steam in order to produce electricity. The controlled speed of the oxidation process, using a redox reactor, affords the opportunity to harvest a combination of electricity and heat, in varying amounts, in a predetermined fashion. In a more controlled device, such as fuel cells and flow batteries, you may eliminate the extraneous emissions, allowing you to harvest more electricity and less heat. Adopting the sliding scale process allows for the management of the optional combustion or oxidation methods, which will then determine the volume and content of the emissions. The emissions that are totally contained in the pipeline are routed for further processing. Now let's consider the Recovery 2.0 strategy in dealing with emissions. The Recovery 2.0 approach would eliminate stack emissions by the total containment and capture of the would-be flue gases and then converting them into a source for the recovery of elements and energy. This would generate a range of harvestable energy with the oxidation of a variety of materials in the form of light, heat, pressure, thrust, and electric current. The adoption of closed-loop mass balance technology, that eliminates combustion emissions to the atmosphere, may provide a virtually unlimited use case for any volume of carbon on a regenerating cycle. In summary, the elimination of emissions from the oxidation or combustion of carbon-based fuels may be achieved through the containment and conversion process into useful carbon-based output products. The CO2 generated from the thermal reduction of waste materials may be a valued resource as a part of a regenerative continuum. By participating in a system that assists in maintaining an energy and mass balance equilibrium, the would-be emissions are allowed to mimic the natural carbon cycle. Recovery 2.0 was developed by Waste.net as a system to manage resources in a sustainable method by treating waste as a resource. If you would like more information about the Recovery 2.0 process, additional videos are available and links have been provided in the comments, or feel free to reach out to us. Waste.net is a tool to assist you by matching waste material generators directly with beneficial users of those materials. By connecting you with market participants, we foster collaboration and promote environmental sustainability. Visit our website waste.net today to learn more. Let us assist you in your efforts to manage your waste. Waste.net may also be able to assist you in finding a market to buy or sell your scrap waste or byproducts.